Thank you. Thank you very much for the invitation to the three of you. Indeed, it's my first time here, and I really feel the magic. So thank you. It's really beautiful. Right, so the talk of my mini course is the algebroid cohomology and ideas in the algebroids. I mean, the goal is to, maybe tell you about the algebroids. I think this is not standard for everyone here, but mostly then tell you about my research on ideas in the algebroids and obstructions to them. And today serves as a preparation. We'll talk about the algebroid. So I give definitions because I've heard that it's, as I said, not known very well by everyone. And then we'll talk about the algebroid cohomology because that's needed for my obstructions later. And then we'll talk about recent research with my PhD student, Rosa Marchesini, about homotopy invariance of twisted Lie algebroid cohomology. And I see that as an advertisement for going higher, so going to Lie algebroids. I'll tell you why. So this is slightly off topic, but I see it as an advertisement. So that's the plan for today. Please interrupt me if you have any question, of course. So first, as I said, the definition. So I'm going to do a big part of the talk on the board, and then I'll switch to slides when it will become technical, because we'll have huge diagrams that I don't want to put myself on the board. So we start with the first definition. So a Lie algebroid is a vector bundle. Oh, and please remind me when my writing becomes very small, because I was told I have to write like this, bigger than my hand. Right. So it's a vector bundle A over a smooth manifold M, which is equipped with an anchor. So that's a vector bundle homomorphism, or let's write it like this. So rho A to Tm over the identity on M that anchors a Lie algebra bracket on sections of A. So that means that you have your space of sections. So that's an infinite dimensional vector bundle, R vector space, sorry. So I've said infinite dimensional. I think it's the first and only time I say it. So it's equipped with a Lie algebra structure, which could be very wild a priori, but it's anchored along the geometry of the manifold, meaning that for all sections AB of A, and for all smooth functions on the base, you have a Leibniz identity. So multiplying the section B with a smooth function on M, well, just doesn't do this. So your bracket is not C infinity M linear, but you can control the favor to be C infinity M linear along the anchor. So you have to differentiate the function along the anchor of the section A, which is a vector field on the base M, and then you multiply by B, right? So that's the definition. And I'm not going to write a whole list of examples. We are going to focus a lot on two corner cases, namely so maybe, as I said, first the two corner cases First of all, Lie algebras. So if your base manifold is a point, right, then T of the point is just 0, so you don't have, your anchor is trivial. And then sections, then your vector bundle is just a vector space because the base is a point. Your space of sections is just the space, the vector space itself, the elements. And then you just have a Lie algebra structure, finite dimensional real Lie algebra. So, if M is a point, then you are just going to call A G, and you will just get a real Lie algebra. And of course, that corner case is a source of inspiration for a lot of studies or problems that you would look at in the algebroid context. But as we will see, of course, it's not enough because it's a super simplified version of the algebroids. And the other corner case is when A is Tm, and rho is the identity on Tm. Your bracket is just the Lie bracket of vector fields. So that's the second extreme case, corner case, prototype of the algebroid. If you look at this, you will recognize it. In that case, if you just have the Lie bracket of vector field, that's just the Leibniz identity, right? So this is really the model, but both cases are, in a sense, models for the algebroids. And then you have other examples. I'm not going to give details, because otherwise we'll run out of time. But you have, you have foliations on manifolds, for involutive subbundles of the tangent. They inherit, restricted Lie algebroid structure. You can do the whole study of principal bundles and principal connections by looking at the TIA or gauge algebroids of the principal bundles, and everything becomes very neat. So if you are interested, you can always ask me. Then the algebroids have become very prominent, I guess, in the context of Poisson geometry, because the cotangent bundle of a Poisson manifold is a Lie algebroid. And that's really important. So cotangent bundles of Poisson manifolds. And then where do Lie algebroids come from? They were found in the 60s to be the infinitesimal version of Lie groupoids, which will be mentioned in Francesco's talk later. So infinitesimal counterpart of Lie groupoids. That's due to Pradin, the school of Eresman. And then around 2000, Kreinicke and Fernandez found that actually not all algebroids are integrable. So there's a lot going on there, but we're not going to focus on this. Yes, yeah.
As you underlined this corner case, I never thought it this way. So in the other way around, is there a natural regularity condition on A such that A is constructed by Lie algebra plus something like Tm?
Well, if your Lie algebroid is transitive, for instance, meaning that the anchor is surjective, then you will have, you will not necessarily have a splitting, but in some cases, you will have a whole corner, so you have a whole Lie algebra bundle sitting in your Lie algebroid as the kernel of the anchor.
So you have an exact sequence.
Exactly. Yeah. So yeah, I should have said you also have as maybe more interesting version of this case, you have the algebra bundles. That would be where you have a manifold, and then you take the product with the algebra times the manifold as a vector bundle with a constant algebra structure. But you also have bundles of the algebras, so you could also have a manifold with a vector bundle over it, and each fiber has the algebra structure that is valid. That would happen if your anchor is trivial.
I have a remark to this question. So if you start with an infinite dimensional Lie algebra, which is consists of sections of some kind, and you have to assume that the adjoint, the small adjoint, should be a differential operator of first order. Then you can try to split it into zero order part and first order part with respect to something that you could do. So that would be a beginning. Answer your question.
I guess something is known in this direction.
So I didn't answer your question? Did I answer your question?
Yes. Because you underline this. Okay, I think the right context is that you replace the second example by a Lie algebra bundle. Then you can hope for regularity conditions. Of course, it's not generally true, but you can hope for regularity conditions.
The kernel of the anchor at each point has a Lie algebra structure, but that can also vary. So of course, if the anchor has constant rank, then you have the Lie algebra bundle. Right. Yes, so what we are mostly interested in here is Lie algebra cohomology. So let's define it. I didn't give it a number. So when you have the Lie algebroid, then you consider the space of sections of the exterior algebra of A, and it comes equipped with a differential which copies the Drummond differential of, you know what, I think this is really annoying. It's going to annoy the audience, sorry. That's better. So, it copies the Drummond differential of a smooth manifold, and it also copies the Chevalier-Eilenberg differential of the algebra. So, it's right here. The Drummond or Chevalier-Eilenberg-like. Differential. So how is it defined? Maybe, yeah, I'm going to write the definition. So if you have omega k form on A, then dA omega is going to eat k plus 1 sections of A, and it's the sum I equals 1 to k plus 1 minus 1 to the I plus 1. Then you have rho of AI eating omega of A1. You remove the I section and you go to k plus 1 plus I smaller j, I plus j, and then you insert the Lie bracket of AI aj in the first entry. And you remove those later. Right? So if you have the formula for the Drummond differential in mind, this is exactly it. If these were vector fields and the echo was the identity, then that would just be the ith vector field eating the form on the other vector fields. And yeah, that would be the second part, right? So if A is Tm, this is a Drummond differential. If A is a Lie algebra. This is a Chevalier-Allenberg differential. This just vanishes. So Chevalier-Allenberg differential for a Lie algebra with values in R. We'll see twisted Chevalier-Allenberg differentials later. What's important about it is that, well, it satisfies the Leibniz formula, dA omega wedge eta plus -1 to the omega wedge dA eta. And most importantly, dA square equals 0, like in the two corner cases. So we get the Lie algebroid cohomology. So H, bullet A, or let's write the case one. That's the kernel of the dA on K forms divided by, well, divided, modulo the image of dA A minus 1 forms. Right, and again, this copies the Drummond cohomology, the Drummond cohomology of a manifold and the Chevalier-Allenberg cohomology of a Lie algebra. This language is useful just because I cannot really define an object without defining their morphisms, and we need them. So this differential is also useful to talk about morphisms of Lie algebroids. In general, morphisms are quite annoying to define for Lie algebroids. If you look at morphisms of Lie algebroids over different bases, but with this language it's easy. So a vector bundle morphism phi over some little phi. It always defines a pullback on forms. So it defines map on forms. I'm sure that you can guess the definition. So if you have a form on B, then this is going to be K form on A. So you're going to feed it with K sections of A. And then if this is at the point P of M, then you will have omega at phi of P eating phi A1, phi AK. So this is a natural notion of pullback of forms. And then phi with its base map is a Lie algebroid morphism. Well, if it's a cochain map, it induces a cochain map. Right? So if phi star composed with the Lie algebroid differential of B is the Lie algebroid differential of A. I cannot make stars, composed with phi star. Right, so if you have a cochain map, and so if you have an induced map in cohomology. Again, it makes sense for our corner cases. And what I want to say again about the corner cases, yeah, I forgot to write it before. Right, so we have once the RAM differential, if A is Tm. I mean, this is okay because in that context, well, I'm not really sure, but I don't know a lot of literature that would look at twisted Durham differentials, but maybe I don't know it. But in the case of Lie algebras, then, as I said, you have the Chevalier-Allenberg differential as an example of this the algebroid differential. And here, in that context, we are actually maybe not really look at this differential, but as the Chevalier-Allenberg differential with values in a representation, so twisted Chevalier-Allenberg differentials. They are much more interesting. Why are they interesting? Well, for instance, in the study of deformations of all those algebraic structures. So how do I clean the board the best? Should I take this? German way with water? Good. German way again with this not entering the, yeah. Yes. Can I, because that just fits in. Right, so in the context of Lie algebras, there's much more about, as I said, the twisted Chevalier-Allenberg differential. So you would look at representations of the Lie algebra on vector spaces, and you would look at the induced Chevalier-Allenberg differential. And as I said, I mean, I know mostly of its importance in the context of the study of deformations, of the algebra brackets, subalgebras, morphisms, now also ideas. In recent work with my PhD student Ilias Ermedis. And that you don't see much in the other corner case of tangent bundles, I guess. Or you see it less, I would say. But still, for our results, so obstructions to ideas in the algebroids, we need this twisted the algebroid cohomology. So we need to define this. So we are going to define representations of the algebroids. First of all, the algebroid connections. So again, A over M is a Lie algebroid. And then you consider a vector bundle over the same base. And you're going to say that an A connection on E is an R bilinear map. With really, again, you copy the definition of the standard definition of a TM connection on a vector bundle. So multiplying a section of A with a smooth function on M just, is a linear condition. So it's C infinity M linear in the first argument, and in the second argument you have a Leibniz rule. Right, so again, it's just copied from the corner case of tangent bundles, but also if A is a point, if M is a point, E is then a vector space over the point, or just a vector space, then that would be, the basis of a representation of A, right? So that would actually be, in that case, just a map from the vector space A to the vector space of endomorphisms of E. And then it's going to be a representation if it has no curvature. So nabla is a representation of A on E if R nabla A1, A2E, which is defined by nabla A1, nabla A2E minus nabla A2, nabla A1E minus nabla A1, A2E is 0 for all A1, A2 sections of A and for all E and E, right? And this is in general a two form on A with values in endomorphisms of E, which is defined by this equation, right? So again, in the corner case given by the algebras, this is just a representation. And well, I guess in the corner case given by TM instead of A, well, this is a flat connection, which is also something strong. Yeah.
Define it as a morphism from A into the Lie algebroid of derivations of A.
Yes, of E.
That, which is more close to the standard definition.
Of course, but I don't have that much time. It is my slide, but I
Okay.
cut it. Right. Of course, yeah. So you can define it as a Lie algebra homomorphism to the derivations of E, and the derivations of E is a infinitesimal, is a Lie algebroid of big GL of E, which is the Lie groupoid of morphisms between the fibers of the vector boundary E. Francesco is going to talk about that. Oh, yeah. Right. So this gives us now the twisted differential. So you have now D nabla forms on A with values in E, two forms on A with values in E. So what do I mean by this notation? This is wedge bullet A star tensor E. So how is it defined? You have D nabla of E is nabla.E, which is then a one form on A with value in E for E, a zero form on A with values in E, which is just a section of E. And you have this, and you have a Leibniz rule with respect to the algebroid differential.
Still a differential. It's D nabla. I mean, this square is equal to 0.
Not yet.
Yes, not yet.
Yeah. So you can define it for a connection, and then if the connection is a representation, it squares to 0 and defines the cohomology. Right? So you have what did I want to say? Right. So you can define it like this. You have omega in A form. You can wedge it with an A form with values in E, and then you have a Leibniz rule. dA omega wedge eta plus -1 to the omega wedge d nabla eta. And actually dA itself is an example for d nabla where you have the representation of A on R, which is just given by differentials of functions, which is right. So, and then if, well, maybe we'll get into those details later, Thursday. But then you have that if nabla is a representation, then d nabla squared 0, and then you get the twisted the algebroid cohomology, which is then written like this, right? So
No? Blah blah the representation if and only if
Yes.
DAs. Yeah.
Let me change some words. Yeah. If you want. Yeah. Because d nabla square is just the curvature. But we'll get back to that in a couple of days. So we get the E-twisted the algebroid cohomology. And as I said, in the case of the algebras, that's super standard. In the case of tangent bundles, maybe a bit less. But if you look at the case of tangent bundles, and even if you forget, first of all, about the twist, then an important property of the RAM cohomology is that it's homotopy invariant. Right? So if you have two homotopy equivalent manifolds, they will have the same de Rham cohomology. Or if you have homotopic smooth maps between manifolds, they define the same morphisms in cohomology, right? So so it is a homotopy invariant. And the question that we're going to answer in the second part of this talk is, what about twisted the algebroid cohomology? And actually, first of all, what about twisted de Rham cohomology? Because that's actually also new. So what about twisted de Rham cohomology? And what about well, twisted or not, that's new in both cases, the algebroid cohomology. And as I said, I want to advertise a bit the algebroids. Well, I don't know if I said it, but I said it at breakfast. I want to advertise with this case here, I want to advertise this going higher to the algebroids instead of staying in a smooth world of smooth manifolds, because I hope I'm going to convey or show you how it is actually really necessary to go to the world of the algebroids to solve this question, which still seems very standard. So is the twisted de Rham cohomology homotopy equivalent, invariant? Well, yes, it is, but you have to, you cannot solve it in the world of smooth manifolds only. Right, so I just do a little bit of preparation and then we'll use slides as well. Because I guess the first question is, well, what is a homotopy? What is a homotopy of the algebroids, right? This was also a little bit obscure in the literature. And that's what my PhD student, Rosa, really was obsessed with good results. Right, so some preparation. First of all, when you talk about connections or representations, we need to talk about gauge equivalence of representations. So if you have, again, A over M is a Lie algebroid, and now you have two smooth vector bundles over the same base, then two A connections, nabla on E, and nabla prime on E prime. Are called gauge equivalent. If we have a morphism, so yeah, if you have an iso or vector bundles over the identity, such that, so theta, let me think, doesn't matter. So theta minus 1 of nabla prime A of theta over section E is nabla AE for all A section of A for all E section of E. Right, so up to you have an isomorphism, and up to this isomorphism, the connections are the same. Well, seems like yeah, pretty standard the definition, but we'll need it. So if you have this, your connections are gauge equivalent, and then if well, let's say like this, nabla is flat, or nabla is a representation. I didn't really talk about flatness. If and only if nabla prime is a representation, and then theta, of course, because everything is isomorphism, defines an isomorphism in cohomology, right? So how do I name it? Just theta star. Theta star from the, oh, sorry, I forgot an important part of the notation here. Nabla. So from the twisted cohomology of A with values in E to the twisted cohomology of A with values in E prime, and you just send a form, class of a form, to theta composed with the form. I leave it as an exercise. I mean, yeah, it's just an isomorphism. It's well defined and everything. Right, so we call that a gauge isomorphism.
So if E is E prime, and this is just an automorphism, yeah? So do you get identity, or this could be some non-trivial isomorphism?
Well, it could be non-trivial. Why would we get the identity?
Depends on if you're in the component of the identity. If your isomorphism is in the identity, in the
okay, so this
connected component of identity
related to homotopy
identity. But if it's not, it might or might not.
Okay. Well, I don't know why it should be the identity homology.
No, if you have the connected component.
We don't have the homology. But I mean, the adjoint cohomology is not exactly like the Ram cohomology.
No, in his case, if you have an automorphism, is in the connected component of the identity of E to E. Then this induced map should be identity. But you have the group of components.
I guess so.
You have the discrete group of components which act there, and it might or might not give identity.
Yeah, okay. You mean it this way, then yes. I will do that.
H0, is it simple to say what this? So H0 nabla AE in general? It's
No.
okay.
Covariant
And
constant sections.
actually, I'll tell you later, we had a bit surprised. Last week and we didn't solve it yet. So it can be really strange.
No, H0 should be the covariant constant sections.
What?
The covariant constant sections.
Yeah.
Nabla E equals 0.
Yes, well, by definition.
Yes, by definition.
Yes, but depending on the case, we decide what it is. Okay.
Well, it's like the round homology.
Yes.
So they enumerated about homotopy times of automorphism, roughly, yeah?
Yes.
No, okay.
Right, let's continue, otherwise I will run out. Yes, you have used your question time. So now, if we have the algebroids and a morphism between them, and if you have a linear connection, then the pullback of nabla under phi is the linear A connection on the pullback, what's it called? Yeah, the pullback vector bundle E is defined by, well, like you would define it. So nabla at a point A, which is based at P, of a pullback section. So AP is an A, E, and E is a section of E. You can pull it back to a section of phi pullback E, and those sections, they generate the whole of the pullback. And then this is the element of the pullback given by phi A at P of E. So you can check that this defines well-defined connection on A, and it also does D. So we don't talk about a flat connection yet. Don't talk about a representation, but you have some wants to be cochain map then. So if, so that leads us to the pullback of the form nabla being R of the pullback connection. Seems standard, but you have to check it. And so if nabla is a representation, then also the pullback is a representation, and you get a map again in cohomology. So this time in twisted cohomology, which we write like this. Phi pullback nabla A on phi pullback E. Right. Oh, I was hoping that I didn't need to clean about. Okay. So I just write the definition of the homotopy equivalence, and then I'll show you the result. Or maybe I'll do it.
R is in honest truth a mixture of big phi and small phi.
Well, small phi is its base map, so it's part of the data.
Yeah, you have to get big phi.
Right, so now what is a homotopy of the algebroids? It's a very difficult question because the algebroids have been around for a while now, but in some literature, homotopy is defined strangely, and in some literature you can say that the algebroid cohomology is not homotopy invariant, which is not true, but it's mostly due to the fact that this homotopy was not defined, not prominently maybe defined properly. So, definition 1.5. So if you have
5.6.
You're very sensitive. So if you have two algebroids, then if you have two morphisms, let's write them like this. So phi and phi 0 and phi 1, sorry, A to B, over e to the phi 0, e to the phi 1. They are LA homotopic. So LA, of course, stands for the algebroid homotopic. If you have the algebroid morphism, so from the product Ti times A. I didn't say that, but if you have two algebroids, you can define the algebroid is not a product. That's pretty straightforward. Yeah, pretty straightforward, but I guess a bit technical when you define it precisely. But I think it's okay to just say it like this. So, if there exists a Lie algebroid morphism phi from Ti times A to B over a smooth map from I times M to N, such that phi composed with I0 from A to B is phi 0. I'm going to say in a minute what I0 is. And phi composed with I1 from A to B is phi 0, phi 1. Right, and Ij is the map from A to Ti times A, M I times N. That just copies what you would do on the base, right? So you send A, at a point P, let's say, to the 0 at J, AP. That's obviously over P. And then you have the standard inclusions for standard homotopies, right? So those are the algebroid morphisms. That's one of the properties of this product, right? So the definition is pretty straightforward, but somehow it was missing. Maybe let's be a bit hand wavy, or maybe let's write it here. So first of all, A and B are homotopy equivalent. If you have I, A to B, psi, B to A, such that psi composed with psi is homotopy equivalent, homotopic, sorry, to the identity on B, and psi composed with phi is homotopic to the identity on A. So, makes sense. And also, here I will just say it with words. You can ask me later. In a case where A and B are just tangent bundles, then, well, there's actually an anchor condition for the algebroid morphism, which I didn't write down because it was contained in this definition. But if A and B are tangent bundles, then this phi has to be the tangent of phi. So we just have the standard notion of homotopy of smooth manifolds. It's just that the whole information is here, and that's the tangent. And if A and B are the algebras, I'm skipping this, ask me later, we actually have the notion of homotopy being super restrictive. So for instance, two LA homotopic Lie algebra morphisms to an abelian Lie algebra have to be the same, have to be identical. And that's a special case of the fact that LA homotopy of morphism is phi 1 being a smooth deformation by Lie algebra morphisms of phi 1 or phi 0. Sorry, not only smooth but trivial deformation, right? So you just have to solve a differential equation. I will ask Karl Hermann about it later. Anyway, so let's keep that and finally connect my computer. Show you the main result here. Do we need to change the light? Right. So Rosa's PhD thesis, which will be completed this year, is dealing with this homotopy of the algebroids. And one of the main results is the homotopy invariance of twisted Lie algebroid cohomology. So if you have two LA homotopic LA morphisms, then you can show that they induce the same map in cohomology, which, as I said, was not even known for twisted de Rham cohomology. And I want to give you an idea of why, maybe. Right, so you have your two morphisms from A to B. They are going to define two maps in cohomology. Or maybe I should have put, yeah, actually there's a bar here, but it's just notation. They will define two morphisms, of course, to different spaces, right? The twists are in different vector bundles, phi 0 pullback E, phi 1 pullback E. But the statement is that you always find a gauge equivalence. Sorry, yes, but we're going to stay there. Oh, the pointer, thanks, yeah, thanks. You always find a gauge equivalence between, oh, wrong notation, sorry. That's another phi. It's the same phi. You're always going to find a homotopy equivalence, sorry, a gauge equivalence between the connections so that this diagram commutes and you have the same map in cohomology. The proof is rather long, but I will just give you the key. and the diagram. So the key is to construct this gauge equivalence, of course, and then everything follows from it. Oh, and the other key, sorry, another key is well, generalization of this. Well, if you look at it, if you think about A as Tm, and you forget about F, you forget about the twist, just cohomology with values in R, then this is a standard result in bot and 2 that if you have I times M, the projection M, then it induces the identity in cohomology, right? The I, well, it's just a homotopy, nothing happens, right? So this is a generalization of it. If you have A, so Ti times A to A, and then the projection on A, which is over the projection on M, again, that's a Lie algebroid morphism. And the first thing you need to check is that with or without twist, this projection defines an isomorphism in cohomology, in twisted cohomology. That proof really is just adapting Botton 2. You take the book of Botton 2, you adapt, it works, right? So that's not complicated. And then you get a huge diagram. It's very small because because it's big. So you get your where is it? So you get your two. Sorry, it's not yet where we are. Well, let's not get the end diagram. But if you take a Lie algebroid Ti times A and the twisted cohomology with values in the vector bundle F, then you can restrict. You can look at the restrictions as before to special times. So you get Lie algebroid morphisms A to Ti times A just by choosing a time. That they give you contravariantly morphisms in cohomology, time T, time S, and you have to make this whole diagram commute. So those are those two inclusions, defining those maps in cohomology. Then I'm going to tell you how this gauge equivalence works. And you also have, you also construct isomorphisms Ti times A with values in F to Ti times A with trivializing F, right? So F is a vector bundle over I times M, so that you can always twist to I times the vector bundle over M. I mean, that's actually classical smooth manifolds, but we have to do it correctly. So that also defines isomorphic spaces or gauge equivalences. You just define those connections on those spaces, and then you have this Botton 2 thing. So you have a huge diagram commuting, and at the end, you find that, well, you check that everything commutes with those restrictions and so on. Whatever it is, also in 3 hours, there would not be enough time to talk about it. I just want to tell you how this gauge equivalence is defined. So the key, or maybe I'll tell you tomorrow, right? So tomorrow I'm going to tell you how this gauge equivalence is defined. It's okay, I was expecting running out of time. And I will show you why it's really important for this kind of thing to leave the world of smooth manifolds and look at Lie algebroids, because this gauge equivalence really uses Lie algebroids. Yeah, sorry, this is a bit messy, but I'll give you the sketch of proof tomorrow, because